Okay, so time to finish up chapter 4 on least squares. So we have one last least squares problem to talk about, least squares of linear constraints. But as a sort of prologue to that, what I'm going to do is talk about a more general problem. So instead of trying to minimize a specific function with respect to specific constraints, I'm going to talk about minimizing a general function subject to more general constraints, which is actually something I teach about in Cal 4, but doing it this way helps better helps create a better understanding of the method involved and why it actually works. So I think this is a mini lecture. Hopefully, it really is a mini lecture on the method of Lagrange multipliers. Okay, and this is actually written up in my Math 280 notes. That's the multivariable calculus or Cal 4. So I'm just pulling out material for this. So the goal is to minimize some given function f of x that maps n variables in x to R. So in other words, x is in Rn. And then we have subject to constraints g of x is equal to 0. Now, g is a function that maps Rn into Rp. So we have, that's a vector equation of p equations in it. So we have p constraints on the n variables, and it's, p is going to be strictly less than n. Just because the idea is we have infinitely many x's that satisfy the constraints, and we want to find the solution from that set that makes f as small as possible. Now, for convenience, I'm going to write out the constraints in terms of components. So g of x has component functions, g1, g2, gp, all of which must be equal to 0 at the solution. Okay, so each one of those is a function of n variables. So gi maps Rn into just R. Okay. Now, if we were trying to solve an unconstrained minimization problem, just minimizing f by itself without regard to any constraints. Then what I would do is take the gradient of f and set it equal to 0, just like in single variable calculus, take a derivative, set it equal to 0. But that's not going to work in this case because we need a value that's going to satisfy the constraints too. And we can actually use, even though it's a calculus problem, we actually use linear algebra to help us solve it. And you'll see that in a little bit. Now, I'm going to give you an example of constraints. So let's suppose we're operating in three-dimensional space. So we have a g1 of x, y, z will be equal to x squared plus y squared plus z squared minus 1. So we set that equal to 0. The set of x, y, z that satisfies this constraint is just the unit sphere. Center of the origin, radius 1. Now make up another constraint. It'll just be x plus y plus z minus 1. That must also be equal to 0. Now, the solution set of that constraint is a plane. So we have a unit sphere. We have a unit sphere, and then we have a plane that's cutting through it. So the intersection, so instead of all points, x, y, z that satisfy both constraints is the intersection of the unit sphere and this plane. So it's going to be So I would draw that. You have some plane coming through it. That would make like a ring of some kind. So it's this set that we care about. So we're trying to find within this set the minimum of f. So an example of f might be, like for instance, just its Euclidean length. Like what if we try to find the point on this ring that is closest to the origin? So function f would just be square root of x squared plus y squared plus z squared, Euclidean length. And then these constraints must both be equal to 0. So that's an example of this kind of constrained minimization problem. So since we can't just set the gradient of f equal to 0 and solve it, what do? Well, really what we like is, instead of the entire gradient of f, in other words, all partial derivatives of f equal to 0, we want f to have a 0 rate of change, not in the whole space, not in every direction, but just directions that keep us within this set of points that satisfy the constraints. So put another way, each constraint, gi of x is equal to 0, defines what's called a hypersurface. So it's a surface in n-dimensional space. So if n is 3, it's just an ordinary surface. So the set of all points that satisfy all the constraints is an intersection of these hypersurfaces, like we have right here. So now the thing is, on each hypersurface, each gi, each component of g, has to be constant. It has to be equal to 0. So what that means is the directional derivative of gi in a direction of u, which is the same as the gradient of gi dot product or transpose u, must be equal to 0 for any u in the tangent space of this hypersurface. Okay, so if u is in the tangent space of a hypersurface defined by this constraint, then it must be orthogonal to the gradient at each point on the surface. Okay, because if a derivative in its direction is 0, that means that g is not changing in that direction. G is remaining 0, which is it's supposed to. Okay, so now let's take all constraints into account. If u is in the intersection of all the tangent spaces, so each tangent space I from 1 to p, if u sits in all these tangent spaces, then the Jacobian matrix of G times u, this is a matrix vector product, must be the 0 vector. Now to see where that comes from, what is a Jacobian matrix? It has the gradients of all the individual constraints as its rows, which is why I'm transposing it. So this dot product I have here, I'm just stacking them on top of each other to come up with this equation right here. So in other words, u is in the null space of the Jacobian matrix, which consists of all partial derivatives of all constraints with respect to all variables. So it's a P by N matrix. Okay. Now, to minimize f within the set of all points that satisfy the constraints, we require that the gradient of that the directional derivative of f, which is the gradient of f dot product with u, must also be 0. So, because the gradient of f is orthogonal to any vector in the null space of a Jacobian, in other words, gradient of f belongs to this subspace. It is, the perpendicular symbol means orthogonal complement of this null space of a Jacobian matrix. Now, we actually know what that is. So for any matrix, the orthogonal complement is a set of all vectors that are orthogonal to every vector in this subspace. So, the orthogonal complement of a null space of a matrix is, in general, is a range of a transpose. So the orthogonal complement of a null space of a matrix is a range of a transpose of that matrix. That just holds in general. So that would mean that the gradient of f is equal to the transpose of a Jacobian matrix times some vector, which I'll call lambda. So lambda is in RP, because Jacobian matrix, this is a P by N matrix, so this matrix is N by, the transpose is N by P. So lambda has to be in RP, and this vector, lambdas, are called the, Lagrange multipliers. Okay. So, to make sure that the gradient of f does not change within the set of points that satisfy the constraints, which means achieving a local minimum within that set of points only and not the whole space, it must satisfy this for some vector lambda. And for any point where this happens, so we have to find all the x's where this happens. And those same x's must also satisfy the constraints. So this kind of problem, like when I sign in Cal 4, it's a real pain. You have a whole bunch of nonlinear equations to solve. You have n equations here for the gradient, and you also have p equations for constraints, and they all have to be satisfied. When they're general nonlinear equations, it's quite a pain. But we're not going to think about this general problem, but I just want to show you why, by solving this equation and including the constraints, we can find x's and lambdas that satisfy both of these simultaneously, then the problem is solved. I'll make sure this is still going, because my computer is doing something funny. Okay, we're good. So, for the rest of today, what I'm going to do is now specialize to our particular problem, least squares of linear constraints, with method of Lagrange multipliers, and show how this set of equations specializes to that case, and how we can solve it quite deterministically, because the equations involved are all linear in this case. With this method of Lagrange multipliers, here's a plus and minus. So what plus is, it allows us to take a constrained minimization problem and transform it into an unconstrained minimization problem, which is good because we know how to solve those. But the downside is we're actually introducing more unknowns, these lambdas. And the thing is, constraints should have a way of reducing a number of unknowns, not adding them. So I will show another approach after talking about Lagrange multipliers, so a very different approach that actually reduces the number of variables. We actually will solve an unconstrained least squares problem. In that case, too, that will be smaller. So that has an advantage of, in terms of efficiency, but it could also, if your original problem is sparse, it could destroy that sparsity. So no method is a clear winner here, but I want to show you these two approaches. Okay, so now I'm going to specialize to case of least squares of linear constraints. Actually, I'm liking the glare situation here. Okay. We'll see if that's better. Well, you can tell me if it's not, I guess. So, this is section 4.5.1 in the book. Least squares with linear constraints. So for this case, the function f that we're trying to minimize is 2 norm of b minus ax from least squares problems. So a is m by n, which is in m greater than n, full column rank like before, which actually I neglected to mention in this section of a book, so I forgot about that. And our constraint function, g of x, is c transpose x minus d must be equal to 0. So these are the constraints. Now, the matrix C involved here is n by p. Again, n is greater than p. And so the thing is, if we're solving C transpose x is equal to d, if it was a square matrix, p was equal to n rather than less than, that would have a unique solution. So the problem would be done in that case. So not an interesting problem. We want a situation where a system is underdetermined, infinitely many solutions, and we want to find which one of those infinitely many solutions also happens to minimize f. An example of an application of this is spline interpolation, or any data fitting problem involving splines. A spline is a function that is defined to be a polynomial on each piece of a domain. So you break a domain down into pieces like subintervals, define your function to be polynomial on each piece, and you want the polynomials to hook together in a way that has the whole function on the whole domain has continuous derivatives, like first and second derivatives. Now your unknowns, like the x's in that case, would be the coefficients of these many polynomials. And you want to relate to these coefficients in such a way to guarantee continuity of derivatives, and that's where these kind of linear constraints come about. So that would be one example of a least squares of linear constraints problem, and you're trying to ensure that kind of continuity, but you also want your overall function to be close to some data vector, like if you have some given y values and you're trying to get as close to them as possible, then that would be what you're trying to minimize. Okay, yeah, you interrupted the recording because I wasn't happy with what followed, so so I was going to do a take 2. All right, I've done a zillion takes in this class, but anyway. So I'm going to apply the method of Lagrange multipliers to this problem. Now, as I mentioned, Lagrange multipliers is a way to transform a constraint minimization problem to an unconstrained one. So now I'm going to be more explicit than before as to how that actually happens. I'm going to define a function called the Lagrangian of this problem. So in general, it's fancy L of x and lambda. So it's a function of both sets of variables, your regular variables x and the Lagrange multipliers. And it's equal to, oh, I should mention This 2 appeared out of nowhere. I should work with a 2 norm, minimizing a 2 norm squared. So be sure to put that in your notes. Squared. That way we're not dealing with pesky square roots. Okay. So Lagrangian is defined to be a function f that you're trying to minimize, okay, plus, now normally what you do, I'm leaving a space deliberately, you'd have the dot product of your constraint function g with the vector Lagrange multipliers lambda. That's how the method is normally described. I'm throwing a 2 in here because then you can just scale lambda accordingly to account for it. The reason for that is when I take a gradient of this, it's going to introduce a factor of 2. So it just makes things cleaner later on. So instead of trying to minimize this subject to this constraint, we can think of it as trying to minimize this function subject to no constraints. How do you do unconstrained minimization? You set the gradient equal to 0. The whole gradient, in other words, partial derivatives with respect to the x's and the lambdas. So I'll write them separately. The gradient in the x variables of L would be equal to the gradient of f plus 2. And then when we take the gradient of this whole term here, well, that's the things we take partial derivatives of the various components of g. G is a vector valued function. That's actually going to introduce the Jacobian matrix. So I'm going to show you how to come up with what I'm going to write here. I'm going to work this out on a component by component basis. So this is the same as a sum from 1 to p of gi lambda I. So now, if I take the partial derivative of that sum with respect to one of the x's, say xk, then I'm going to get a sum of partial of gi with respect to xk times lambda I. But when I think in terms of a Jacobian matrix, that is the same as Jacobian matrix rho I, rows are components, k's are independent variables, or columns are independent variables, gik lambda I. Now this is almost a matrix vector product. It's not quite, because the second index must match, of a matrix entry must match the index, the single index of the vector entry. So I'm going to transpose this and give me ki. So it is Jacobian matrix transpose times lambda, which agrees with, agrees with what I had on the other board, which I've since erased, but you have it in your notes. So this must be equal to 0. The other part of a gradient, partial derivatives of the Lagrangian L with respect to the lambda variables must also be 0. So if I take a partial derivative with respect to lambdas now, I won't get anything from here because there is no lambda. Here I'm going to have 2, and then this is a linear function in the lambdas. What's the derivative of a linear function? It's a constant with respect to lambda. It's just going to, so I'm just going to get g of x. And that must be 0. But all the second part is saying is that the constraints must be satisfied. But we already do that. So now we have to solve this. So this is exactly the equation that I had before, where I say that the gradient of f must be, must be equal to Jacobian transpose lambda. So I'm off by a factor of -2, but lambda is some unknown vector, so that's not really consequential. Okay, so now the goal is to solve this equation, and we're going to take these into account to help us find a solution. So now I'm going to specialize this gradient for our particular problem. So the gradient of f is 2 A transpose AX minus A transpose B. You've seen that before from the when the normal equations were derived. So it's the exact same thing. Plus, now the Jacobian of G is a derivative with respect to x. That's going to be C transpose. So it's going to be C transpose transpose, which will give us just C. And the factor of 2 already factored out. So it's just going to be C times lambda. So that must be equal to 0. And then the constraints, that must be 0. So C transpose X must be equal to D. So I'm just going to erase the 2. Because it's no longer of consequence in what we do. So that is a problem we're going to solve. Really, we're going to solve this equation, and taking this into account along the way will help us to do that. Okay. So now I'll finally be in a position to describe the algorithm and how we can use the solution of the unconstrained least squares problem based on normal equations to, or QR factorization, to get the solution of this problem. Okay. So first I'm going to take that system of equations and rewrite it. A transpose A X. Okay, actually, I think we want to do this. All right. I'm going to leave some space here for the algorithm. Otherwise, I'll have steps scattered all over the board. I don't want that. So as steps of the algorithm are figured out, I'm going to write them here in the proper sequence. And the rest of the board, hopefully this will be enough space, I'm going to use for my scratch work to come up with those steps. This is one benefit of having to screwing up a lecture several times. That hopefully this turns out cleaner. We'll see. So I'm going to write it as A transpose A X is equal to A transpose B minus C lambda. Okay. So what that means is X, our solution X, is equal to A transpose A inverse A transpose B minus A transpose A inverse C lambda. Now, A transpose A inverse A transpose B, this first part here, I'm going to call that X hat. And then we have the rest of it. Well, that is the solution of the normal equations. It is the solution of the unconstrained least squares problem of just finding a minimum of b minus ax, of a norm, a 2 norm of b minus ax. So we already know how to do that. So that's really the first step in our algorithm. Solve the unconstrained least squares problem. And that'll play a role in the solution of our original problem. So I'm going to put that here. But not solving normal equations. I'm actually going to use a QR factorization because that's a better approach anyway. So I'm going to say A is equal to QR. And we're going to use the thin or economy size QR factorization. That's really all we need for the least squares problem anyway. And R will be helpful later on. So what we have here is so A equals QR, and then to get the solution, R times X hats is equal to Q transpose times B. And R is upper triangular, so we can just solve this using back substitution. So now we have X hat. Right, so our algorithm is off to a good start. Okay. Now, the thing is, we need lambda to be able to finish off the process. So what I'm going to do is, I'm going to take this equation here, and I'm going to multiply both sides by C transpose. So I have C transpose X on the left side, but we know what that is. It has to satisfy the constraints. So that must be equal to D, which is known. And that must be equal to C transpose X hat minus C transpose A inverse C lambda. Okay. So this is known, and this is known. We just don't know this lambda. Okay, but now we have a system of equations for lambda. So we must solve C transpose A inverse C lambda is equal to D minus C transpose X hat, rather. Okay, so the right side of this system is known. Now, what about the matrix? C transpose A inverse C. We definitely don't want to compute all of that. We don't want to compute it inverse explicitly. But what can help us to do that is use the fact that A is equal to QR. We have a QR factorization. So if I write out C transpose A inverse C, I fill in the QR factorization for A. So I have R transpose Q transpose for A transpose. That A is equal to QR inverse. Then we have C. Now Q is a matrix that is not square, but it has orthonormal columns. So Q transpose Q is identity. Now while A itself does not have an inverse, I could not, use a property, the inverse of a product is a product of the inverses in reverse order. I cannot do that with A, because A or A transpose individually do not have inverses. But R does. R is a square invertible matrix. So now I can say C transpose R inverse, and then R inverse transpose times C. So now this matrix here, R inverse transpose C, I'm going to call that W. So now this whole thing is equal to W transpose W. So now I've transformed the system I need to solve into this system. So now we have W transpose W is equal to this right-hand side that I have. Okay. Now, I don't want to solve that directly. Now, the thing is, W transpose W, matrix of that form, since everything we have here is a full column rank, that matrix is symmetric, positive, definite. And if you are here, I would ask you how do we solve something like that, but since you're not here, I'll just have to tell you, is use a Cholesky factorization. Now, so we can take, or what we can do is take the QR factorization of W, and that would actually give us a transpose of a Cholesky factor, which is fine too. So here's what I'm going to do. I need W. So W is equal to R inverse transpose C, which is the same as saying R transpose W is equal to C. In other words, we have to solve that system. So I'm going to write that as the next step in my running algorithm here. Solve R transpose W is equal to C. Now, R is n by n. C is n by p. W is also n by p. So I'm solving p systems of linear equations using the lower triangular matrix R transpose, so I can use forward substitution. So this step is pretty cheap. So the cost is going to be in the order of n squared p for that step. Whereas this is going to be, so QR factorization of that m by n matrix, but it's a thin QR factorization. So it's going to be order mn squared. Okay. And this is going to be back substitution order n squared. Okay. With n which is greater than n, which is greater than p. Okay, so now I have w. So the next thing I'll do, to set up solving a system involving w transpose w, what I can do is a QR factorization. So w is equal to pu. That is another thin QR factorization. So p has orthogonal columns, so p transpose p is identity, and u is upper triangular. So as a result of that, w transpose w becomes u transpose u. Oh, I goofed here. I forgot the lambda. So lambda has to equal all that. U transpose u lambda is equal to d minus c transpose x hat. So what I'm going to do is I can take this vector u lambda, which is not yet known. Let's see. Okay. I'm going to call it y. So now I can say that u transpose y is equal to this. I can solve that system. U is upper triangular, so u transpose is lower triangular. It's like when you do the, you're solving x equals b, with Gauss elimination, you get your LU factorization. You solve Ly equals b, and then ux equals y. It's that all over again. So we solve a lower triangular system followed by an upper triangular one. We solve this actually with the Cholesky factorization algorithm also. So I can fill those steps in. I can solve u transpose y is equal to d minus c transpose x hat using forward substitution. U is a p by p matrix, so this is on the order of p squared, so this is the cheapest step we've seen so far. And then we can solve u lambda is equal to y. That's an upper triangular system solved by back substitution. The work there involved is order p squared. So then, finally, we can solve for, we can, let's see. Oh, so we have lambda now. So we need to compute this term here, A transpose A inverse C lambda. But A transpose, okay. We don't want to do that as written, because we don't want to borrow A transpose A inverse. So A transpose A inverse C lambda. Well, A transpose A is the same as R transpose R. So it's R transpose R inverse C lambda. So if we write out what this is, keep in mind that R and R transpose are invertible. That's the same as R inverse transpose C lambda. But R inverse transpose times C, that's W. I already have that. So that's R inverse W lambda. So, so this vector that we're looking for, I'm going to call that Z. All right. So that's the same thing as saying RZ is equal to W lambda. That's what I'm solving. So I'll fill that in my algorithm. So I'm going to solve RZ is equal to W lambda. That is back substitution, or n squared operations. So now, this right here, that's my z vector. So my solution to my constraint minimization problem is x is equal to x hat minus z. So I can fill that in as the final step in my algorithm. So x is equal to x hat minus z. And then I'm done. So, so since m is larger than n, which is larger than p, so the overall cost is bounded by constant times mn squared. This is the most expensive step right here, that initial QR factorization. But the thing is, since constraints are supposed to remove variables, here we just added a whole bunch more, p more, these lambdas. So it's the opposite of what you would think. So while this is an approach to least squares linear constraints, now I'm going to wrap up, thankfully. This is taking forever. How long have I been at it? Okay, this is 22 minutes, and it was, all right, so I've been at it for 40 minutes, so it still feels like an eternity. And I'm sure it does for you too. So now I'm going to present a different approach. We're still use QR factorization and unconstrained least squares, but this is a very different way to try to solve a smaller problem than the original, which is what would make sense when you're imposing constraints. I wonder if I should do the same thing in this case. Yeah, I'm going to divide the board. So the algorithm that I come up with will appear on the left. All the derivations of those steps will appear on the right. And if you think that's a good idea, but I can keep doing that with other algorithms. Okay. All right, so alternative approach. Instead of computing the QR factorization of A, and actually that was a thin QR factorization of A, we're going to compute the full QR factorization of C, the constraint matrix. Now C is n by p. Q is going to be n by n. R is going to be n by p. So for a full QR factorization, it's going to be order mn squared. So I'm going to break Q down into Q1, Q2. R will break down into R1 and 0. So Q1 has P columns, and then this, the other n minus P columns go into Q2. And then we have the first P rows and columns in R1. This is a square invertible matrix. Remember, C has full column rank. So, okay, that is the first step of my algorithm. C is equal to QR. Now, if I were to carry out this multiplication, I could say C is equal to Q1 R1, which is true. It's just that later on, am I going to? Yes, I actually am going to need Q2. So that's why it's required in this case to compute the full QR factorization, not the thin one. So you cannot use Gram-Schmidt for this. Probably wouldn't want to anyway because it's not a great method. But so you need to use like either household reflections or Gibbons rotations. Okay, now we've QR factorized C. What does that mean for the constraints? So look at the constraint equation. C transpose X is equal to D. If I fill in the QR factorization there, I get R transpose, so R transpose Q transpose X is equal to D. But that would mean I'd have R1 transpose 0, Q1 transpose Q2 transpose X is equal to D. So if I carry out this multiplication, what I get is R1 transpose Q1 transpose X is equal to D. So now what I'm going to do is I'm going to call this vector U. So R1U, R1 transpose U is equal to D. So that's something I can solve for using, in this case, it's going to be forward substitution because I have a transpose. Okay. Now, so that'll be the second step of my algorithm. So I'm going to solve. All right, so this takes order mn squared. I'm going to solve R1 transpose U is equal to D. So that's on the order of p squared computations, because the p by p lower triangular system solved using forward substitution. Okay. Then what I'll do is, okay. If I look at Q times X, or Q transpose times X, so that'll be the same as Q1 transpose Q2 transpose X. So that's the same as Q1 transpose X, Q2 transpose X. Well, Q1 transpose X, that's U. And I'm going to define Q2 transpose X to be B. All right. So now that I've taken the constraints into account, we're solving this system to get this vector U. What I need to do now is look at what I'm trying to minimize. So the norm of B minus AX. Now, I can write that as B minus A Q transpose X, because Q is a full square orthogonal matrix. So Q transpose Q is identity, Q transpose is also identity. Now Q transpose X I have here. So, so I have B minus A, and then Q I'll break into its two parts, Q1, Q2. And then I have Q transpose X written right here. So that's going to be UV. So now I have B minus, if I carry out all of this matrix multiplication, so I would have A Q1U, so minus that, and also minus A Q2V. Because this product here, you can think of it as kind of like a dot product involving these blocks. Q1U plus Q transpose, sorry, strike that. Q1U plus Q2V. Then you multiply all that by A and subtract. And that's exactly where this comes from. Right, so let me just write that down. That is Q1U plus Q2V. And all of that is multiplied by minus A to give me this. Okay. Now, I have this already. I'm going to put this in parentheses because this part is known. And for convenience, well, let's see. Do I need to do that? I'm looking at the way I have the algorithm written in the book, and it introduces more symbols than I really need. Okay. So I'm going to call this vector in parentheses, I'm going to call it C. So I'm going to add that to my algorithm. So C is equal to B minus A. Oh, do I need that? Oh, okay. Yeah. I can't do that yet. I mean, that vector is going to come in handy, but this vector Q1U I am going to need. Okay. All right. Fine. So I'm going to let Z equal to Q1U. Okay. And I will also define A2 to be A times Q2. Now this is going to be, okay, Q1 is going to be n by p. U is a p vector. So this is going to be order NP operation, so it's pretty cheap. This is going to be more expensive, multiplying a matrix here. A is m by n, and Q2 is n by n minus p. So this is order mn squared, same as the QR factorization. So that's one of the more expensive parts of this. Okay. So what I'm now trying to iron out here is using the new symbols I've defined, minimize B minus AZ minus A2 B, 2 norm. Okay. So this part is known. I'm going to call it C. So now what we have is we're trying to minimize a residual vector. Before, normally it's B minus AX. Well, this is playing a role of B. This is playing a role of A, and V, my unknown, is playing a role of X. So, so this is unconstrained least squares problem. Okay. Now, here's the difference though. V is equal to Q transpose X. But the thing is, so what that means is V, so P components. V has N minus P components. So, whereas with Lagrange multipliers, I was all solving an unconstrained least squares problem involving N variables, all N that I had. Here I'm solving an unconstrained least squares problem in N minus P variables. And this is exactly what you'd expect. If you have N variables altogether, you have constraints imposed on P of them that should reduce it to a problem in N minus P variables. And Lagrange multipliers didn't do that, but this approach does. So I can solve it by whatever means. So like using QR factorization or normal equations or whatever you prefer. So I'm not going to go into the details of that. We know how to solve that problem. So, well, first up, my notation. C is equal to B minus AZ. And then we solve the problem minimizing the 2 norm of C minus A2V equals minimum. And the solution of that is V. Okay. So now I don't have X, but what I do have is Q transpose X. Q transpose X consists of U and V. And now I have both of those pieces. So how to put that together to get X? Now, if Q transpose X is equal to UV, well, Q is an orthogonal matrix. So all I got to do is multiply both sides by Q on the left. So I get X is equal to Q UV. Now, Q has its two parts, Q1 and Q2 times UV. So I write that out, the product. And that's equal to Q1U plus Q2V. But I know what Q1U is. I have that already. That's Z. So X is equal to Z plus Q2V. So now I can fill that in as my final step in my algorithm. So X is equal to Z plus Q2V, and yep, thankfully that agrees with what's in my notes. Okay, so that's just a simple matrix vector multiplication, so it's quite cheap. So this is going to be, the order complexity of this is going to be, or let's see, the order of running time will be, so A2 is going to be A times Q2. So this is a M by N minus P matrix. So this is going to be difficult to express, like, and C is going to be an M vector. So the total work involved here is still, it's going to be bounded by Mn squared. It depends on how large P is, how many constraints you have. The more constraints you have, actually, the smaller this problem is. But then other stages will be more expensive. So order Mn squared expresses the running time of a whole algorithm. It's a crude upper bound, but it's accurate. Okay, so this approach, it has you solving a smaller unconstrained least squares problem, and another thing is because we have the matrix involved is A2 instead of A, and the thing to keep in mind here is that the condition number of A2 is less than or equal to the condition number of, actually it doesn't matter which norm you're using, because in a sense, you can think in terms of A2 as removing columns, if you will, in a certain space from A, or it's like only taking certain columns from it. So that tends to have the effect of reducing the condition number. So you're solving a better conditioned and smaller least squares problem. The unfortunate thing is that if the original constrained least squares problem with X equals B is sparse, then from computing all these entities in here, you tend to lose that sparsity. For example, in this step, A times Q2. So whereas you don't have that same issue with the method of Lagrange multipliers. So it really depends on which kind of, whatever properties of the problem at hand. For instance, if the number of constraints is close to the number of variables, then this problem is nice and small. So you might find that appealing. So there are a lot of things to think about here as to which approach you take, but but at least you have viable approaches with complementary advantages. So, so for your particular problem, hopefully you have something that works well, one approach or the other. Okay, so at long last, that's the end of chapter 4. So the next item on the agenda, which I'll cover, well, tomorrow, because today is Tuesday, is some iterative methods that were not covered in Math 561. So Krylov subspace methods, starting with the method of steepest descent. So I will see all of you tomorrow.